That actually wasn't planned at all. But I felt like that you guys are like hungry to do that. Okay, so that's why we did task number 2. And the idea was to simulate an artificial sample of data from the model. Okay, so we learned how we can do that. That is, we took the nk.mod file and then we put into the stock signal command an option, namely periods equal to 1000, which does have where Daniel simulates the model for 1000 periods going forward. Okay? So that's what we did in the second task. And we looked at monetary policy shocks only, and then we learned a little more about coding up plotting the time series and producing a scatter plot and computing correlations between inflation and the output gap. And then we reproduced the quantitative results that we have on our second slide deck, NK2, namely that with monetary policy shocks only, the Phillips curve is an upward, it's a linear upward line. That's what, so to say, we learned from that. And we covered that in theory on Tuesday and Wednesday, and this is the exercise where we actually learn what's behind those graphs in the slide decks. So that was this task number 2, and then yet another task where this was on the fly, which is now we went to incorporating, so to say, into this model. We learned how to extend the model, in the sense of incorporating the so-called cost push shock in the mod file. So that's something that will come up in research all the time, either when you're writing research papers, when you're writing your thesis. It's often the case that you want to extend an existing model, and of course you can start from scratch, or you can take an existing piece of code and extend that gradually. Okay? That's how I typically do things, that I don't, with hundreds of codes, I don't start, from scratch often. It's like, you go incrementally. And we learn how to do that, actually, right? And we were pretty successful in doing that, I think, right? So we put in that shock, and then we computed the impulse responses for this cost push shock. We computed the scatter plot. We learned that this cost push shock has a negative correlation. And then in the end, we switched on all the shocks, the policy shock, the technology shock, and the cost push shock, and we got that, shotgun blast, picture of inflation and the output gap in the data, right? So at the, lo and behold, we got those dot plots, dot clouds, from our code that we worked with. So that was Friday. That was Friday in terms of what we accomplished. Good morning, Lynn. Hi. So that was our Friday class. Are there any questions that came up after class? No good? Okay. So then what's the plan for today? Well, the plan for today is to work a little bit with the codes underlying the macroclimate model. Okay? So let me go back here. Okay, the task is now to say, okay, since we are all now pros when it comes to working with Daniere and MATLAB, right, why don't we dump this model into Daniere? So this is where we've been busy with until Thursday afternoon, coming to terms with that the macroclimate model of Saluc, Fernandel, and Smets, right, can be written in these 4 equations. There is the IS curve, there's the Phillips curve, there's the monetary policy or Taylor rule, and there is the climate constraint or the climate change equation. And those 4 lines, right, are equations. And we learned last week that this model has a couple of novelties relative to the baseline model that we studied. First of all, the climate change constraint wasn't in the baseline model, where the amount of carbon, the stock of carbon in the atmosphere, is a function of economic activity, abatement, or, spending or taxes, and so forth, right? We also learned that we can read off qualitatively climate-inflation from this model, namely because of the stock of carbon deteriorating productivity in this economy, it means that marginal costs are going up when climate change does happen. And that was the so-called climate-inflation effect. And then we have also a government in this model that can impose a carbon tax, an emissions tax. And when the government does that, first of all, there's a key result, namely when the government does put in a carbon tax, firms find it optimal to abate, to mitigate their emissions. That's the first key result. But of course that is not coming free of charge. When you have that, you're going to have the so-called greenflation channel in the model, that this mitigation spending is costly, it's going to create more demand, and or these taxes are going to create the higher marginal cost for firms, right? So there's more demand for abatement spending, and there is higher marginal cost, both leading to an additional rise in inflation afterward. So that's the model, and then the question now is, how do we get that model into the codes? Now, when you look closely, this model has like 5 trends, right? There is a trend in inflation in the target, there is a trend in this decoupling, there's a trend in technology, there's a trend in population. I believe there's another trend somewhere, I have forgotten about this right now, but there's in total 5 trends in this model. And the trends are like important because when we want to estimate the model against the data, we need these trends so we can explain the data. But they're also clouding the picture of how does this model work in terms of, say, impulse responses that we have been studying so far. Exactly, the transmission, right, Lynn? Right? How does the transmission work? So that's why I put together a code kit for you guys that's called NK Model No Trends. So I literally took out the trends from the model, from the code, so that we can understand how do you set up this model, what are the differences to the new Keynesian model that we started on Friday in terms of computer codes, and how do you solve this model and so forth. And then I also posted the replication codes. So in this folder you have the replication codes from Sahuk, Fermandel, and Smets. And we will see how much we can take a look at that given the time constraints. But I want to work with you now with this. So if you open this folder, there's going to be 2 functions in it. Okay? There's going to be two computer codes in it. And I want to work with you on those 2 computer codes. And that's the basic idea. So let's take a look then at the no trends codes. And I want to arrange maybe my screens here so we can maybe look at that in parallel to the extent possible. Okay. All right. So here is the no trends code, okay, that we have in terms of our model. Okay. So we have, if you have downloaded that, we have 2 files in it. We maybe delete all the unnecessary files. There, right? So when you open this, when you download this folder, please download it, go to your computer to the place where it sits, and then you have 2 files. One is a mod file, and then interestingly enough, there is also an M file. So that's a dedicated MATLAB function, and we'll talk more what that does, all right? But the most important thing for now is to open this nkc_notrends.mod. So please open this into your MATLAB editor, and then I want everybody in the first place to run this file before we try to understand what it does. I want to make sure everybody has a code that runs on your computers. So then please type in diner, and it's all case sensitive, so nkc_notrends.mod semicolon, right? Type that in please into your MATLAB, and then hit enter. And then hit enter, and let's see what happens in terms of this. So there's computations on the command window, and at the end of the day, you should have a picture that looks like this. So that's the proof of the pudding. If you're getting a picture that looks like this and some screen output, then you're golden to get this. So let me ask Anne, how about you? Do you get that picture from your computer? Not yet. Do you have a mistake, like an error message? Oh, I see. So let's see what the error message is. So what do you want? Oh, I see. I see. Can you type it into a command window? Can you type in VER? So bear. No, in lowercase letters. E, like ER. Exactly. That gives you what you have installed. I see. You have installed the basic library. I will talk about that in a second. So, who else? When you run this code, do you get? Do you have the graphs perfect? How about you, Mimi? Must be a mod file. This one. And then make sure. So make sure, so here's a good exercise. When you're having trouble running this, make sure when you want to run mod files in general, with Dynair, that this path, make sure that the path that's shown at top here, this is the working directory. This is where MATLAB is working. That this path is the same as the editor path where your mod file is open. So those two paths must be identical. Okay? Otherwise, you're trying to run a file that MATLAB doesn't know where it actually is. Okay? So try, like what we did yesterday on Friday, Min. We also always made sure that the working directory of MATLAB is equal to where the mod file sits. So let's see what else we got here. How about you? Trying to run it, yeah. Okay. So there's something coming up here, perfect. How about you, Ivy? Having an error message. I see, I know what that is. It's the same as with An, so we'll talk about that. Could I ask you for today that you guys join forces again? Because we will be working a little bit with this code, and this one works on this computer. You need to install something after class today, but not now. Well, how about you? How are things going? Okay, you will run it. Okay. So, how about you guys? Perfect. You have an error message here? It's Monday morning. Okay, NKC. Perfect. Excellent. Anne, would you be willing to work with OAN today? Because you need to install, I'm going to talk about what, but you need to install something after class today. And so could you guys work together for today? Because this one works? Excellent. Dean, how are things going? We're trying to run the NK no trends file. How are things coming here? Oh, I see there's an error message on the optins. Okay, that's not so good, but we'll deal with that. And then how about here? If you could try to run this file, exactly. Just go here and type in here. Let's see what happens. No, not the live coding. No, we don't want to do live coding. You want to download the no trends file from Moodle. So go on Moodle or download this no trends thing, okay? The no trends code, and then. All right. So maybe for Min, Anne, and Ivy, you got an error message. Okay. So the error message that you guys have gotten is that when you installed MATLAB, you didn't install all the toolboxes that you typically need. Right? So MATLAB is, think about MATLAB as being a pocket calculator. And in that pocket calculator, you can do basic operations. But then MATLAB has so-called toolboxes for specific tasks. Okay? So there is an engineering toolbox that the engineering guys use. Then there is a neural network learning toolbox. Then there's a statistics toolbox. Then there's an optimization toolbox. Then there's tons of toolboxes. And in order to run this file, you need one toolbox, and that toolbox is called the optimization toolbox. Okay? So let me show you whether you can see whether you have that toolbox or not. If you go to the prompt in MATLAB and you're typing in var, like for version. Okay, you're typing in var for version, and you hit enter. Then what you're going to get is you're going to get output that looks like this. So in my case, it says I have installed MATLAB 24B. Here's my license number. And then here's the MATLAB core, and that's the pocket calculator. And then I have installed all these toolboxes when I installed MATLAB. And in Anne's case, and I take it also in Minz's case and in Ivy's case, you don't have all these toolboxes, right? Or particularly what you will need is, for these codes to work, the optimization toolbox. As well, I mean, if you can, you should also have the statistics and machine learning toolbox. But those two are like toolboxes that are used often, and you should add this on. You can add this later, after class. Okay, you can add this after class. Please, after today, that's another task for this afternoon for Min, for Anne, and for Ivy. Add these toolboxes to your installation. Okay? So if you are on a Windows computer, you go to the place where you have installed MATLAB, and then you will find something like install. You double click on that again, and then you can choose add toolboxes and so forth. So, Dean, how about you? Does the node transcode run on your case? So when you run the node trend mod file, what happens there? No. It must be a mod file that you want to open. Can you navigate here to where you have this, where you have downloaded the mod file? No. Can you go to Moodle? This one, exactly. I want this one. Can you open this one? Perfect. Because I just tried this on the, when everybody was in here. Yeah, exactly. You want to open it. Okay, but now you need to navigate to the same folders. Can you just double click on this folder here? No. Double click on this folder. Excellent. So now you run this code. You have the same problem as Min has. Okay. Unfortunately, so you guys could work with Hui and Tu. Okay? So maybe you guys could kind of work together today, because it will be important that you see what's going on. Could you try to somehow? You have the same problem that if you type in there in MATLAB, R, and hit enter. You see, you have done the MATLAB installation, but there is the toolbox missing that we will need, which is this optimization toolbox here. Okay. So install that optimization toolbox this afternoon. Okay. And it would be good maybe if you guys could sit with Tu and Hui, so that you can actually look at one computer. So two people always work on one computer. Okay? Because it will be important for you to understand what's going on there. Okay, good. So everybody has a computer there. And so what do we first of all see here in terms of the codes? Okay. What is the exactly? Alright, so let's go through this then. What is this code looking like? Well, it's a Dynea mod file, so the whole syntax is the same as before. Okay? So we have, as on Friday, we have a block where we define the variables. Okay? And in particular, we're defining, these are like the endogenous variables, if you like, of the model, right? So there's inflation, the interest rate, output, the consumption to output ratio, carbon, marginal cost, and then D, which is the unemployment benefit transfer. Then we have the exogenous processes. So those follow AR1 processes, right? There is the monetary policy, there's inflation, there's the preference and the emissions, and those are exogenous AR1 processes. Then we have the true shocks, and actually there's 5 shocks here, but we're only going to utilize 4, right? But so there is this emissions shock, there is the B shock, like the demand shock, right? And then there is the cost push shock, and then there's the monetary policy shock, and there's one more shock, which is this tau. So what is this tau? Well, the way these authors model this in terms of the code is that they keep this exogenous. Oops. So they keep this tau exogenous. So they keep control over that. Okay? So they assume that this is an exogenous object in the model. It doesn't involve endogenously, but there's government who imposes this tax, and that's what they keep this exogenous in their code. So that's the 5th little thing that you can think of what they have in their code there. So then they have a ton of parameters. First of all, they define this in terms of the symbols, and then they have tons of parameters here. And you may wonder, so where are those parameters coming from? Well, they are coming from the estimation of the model that we're going to discuss after the first break. So those are estimated parameters for the most part, not for all, but for the most part. Those are actually parameters so that the model fits the data best. All right, so then we have the Holy Grail, and that's really the Holy Grail. Right? So here we have the model semicolon, and then we have the end semicolon, okay? And in between we have all the model equations. And now the cool thing is, these are the sorry, I take that back. These are exactly these are the non-linear equations that we have in our slide deck. Okay, so let me go back here. So they literally, everyone, they literally take the equations from this slide, 21. Okay? They take the equations from slide number 21, and they're literally writing down these equations. And they know one by one. And notice, these are non-linear equations. There's no log linearization that's been done. No, first order Taylor series expansion, no head variables, and stuff like that. The complete non-linear equations. So the authors do not approximate their equations. Keep that in mind. And all the squares and all the ratios, everything is just as we see it here, is written up in this code. So a lot of headaches that we typically have is in log linearizing the model. That's not done here. And you have to just be careful in writing and typing and not making any typing mistakes, and then you will get these equations. Those are our 4 new Keynesian equations, and then with the added 2 auxiliary equations. And then finally we have the AR1 processes for the demand shock, for the cost push shock, for the emissions shock, and for the interest rate shock. That's it. There's one little bit of maybe a confusion here, is that this transfer policy, uppercase D, in the code. So this is where this is work in progress. If you look into the equations, this is a lowercase d, which is the same as the uppercase d. Okay? So there's because this is a work in progress, it's not completely aligned yet, basically. Okay? But that's it in terms of the nonlinear equations. Are there any questions? Yeah, exactly. I'm going to come to that next. Okay. So now what you're going to do is that you're going to compute the steady state. Okay. You're going to compute what's the steady state. You go through these equations and you're dropping the time subscripts. Everywhere you see a +1 or you see a -1, you're dropping all the time subscripts, and then you're looking for what's the solution of this model in steady state. Can you solve for the endogenous variables of the model in steady state then? And that's when you are working with a nonlinear model. It's a little different than in the nk.mod that we discussed on Friday. Because now the steady state model is a little more complicated. And in fact, that can be the most work when you work with nonlinear models. because you have this steady state model semicolon and semicolon. So this end actually can go, like this. Okay? So in between the steady state semicolon and end semicolon, you have the so-called steady state equations. So you're working out, you take literally those equations and you write them in a notepad without time subscripts, and you're solving for, what is R bar, the steady state interest rate? What is pi bar? Okay, that's what you do. Now, okay, and then you will find that, for instance, the consumption to output ratio is just going to be this. It's 1 minus mu bar sigma da 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 da. Okay, and so you're trying to solve. The idea is you're trying to provide as many objects that you have in your endogenous variables. Okay? That's the idea. So you have to solve for the steady state in closed form. Now, it turns out that the steady state is a complicated object. In particular, you will not be able to solve the model in closed form for all the variables. So you cannot, for instance, write down C is a function of parameters, Y is a function of parameters, right? That's what we want. We want that all the endogenous variables are functions of parameters. That's that in terms of the steady state. Turns out for output it's not possible to do so, because output is a nonlinear equation. It's so nonlinear that you cannot solve closed form. So this could be various examples are you take any general nonlinear equation. Sometimes you just cannot solve closed form. So we try to make up maybe an equation here on the fly. So some equations like in steady state could look like this. Like you have something like y. You have something like y bar. Plus 1 is equal to the square root of y bar to the cube plus, let's see, minus y plus x squared or something like that. Okay? And actually, there is a solution to that, but you can imagine that if you make this equation much more complicated, you will not, in general, be able to solve for this in steady state right away. That's the basic idea. There are equations that are really nasty that you cannot solve for y bar easily. Because if you square this now, right, on the right-hand side and on the left-hand side, you're going to get a square. So that's, in general, hard to solve in closed form. And that's why with nonlinear models, you will then have often the case that you need to solve for the steady state numerically. Okay? And that's what this line 118 does. So this line 118 says, to solve for output in steady state is so tough, I need a numerical routine to do so. I can solve nonlinear equations numerically. Right? So I can, when I'm not able to solve an equation like this exactly, I can go numerical. I can say, give me x, and then I'm trying different y's until this equation holds. Okay? Numerically, I'm trying y this, y that, and then numerically, I'm getting closer and closer so that this equation holds. Okay? And that's what the authors do. Right. So where do we see this? Well, they are calling a function. Okay? They are calling a function, namely a function that they call steady state NKC. And so in Linear or MATLAB, you can write scripts, but you can also define so-called functions that takes as an input. So that function takes as an input all these parameters. Look at it's a lot of parameters, right? But you are dumping in all the parameters into this function as an input, and the output of that function is the steady state output. That's how this works. And where is this function around? Well, this is exactly this NK steady state, the steady state NKC. This is this function here. Okay? That's why there is this second function. So let's open this function. If you double click, you just go here, you just double click on that function, and then you see, right, this is a function that outputs y, that's the output, right? Once you call the function, and then the function has done its job, it's going to send as an output Y to the place where it was called. And then these are all the inputs. These are the parameters as an input. And then, you're going to search numerically, what is the Y that solves an equation. And for that, you need the optimization toolbox. Right? The reason why Min and Dean, An and Ivy have this error message is that you don't have the optimization toolbox installed. And because of the optimization toolbox not being installed, you cannot run another MATLAB inbuilt function that's called fsolve. So fsolve is a function that comes with MATLAB that is a part of this optimization toolbox. So if you click and you just type in help fsolve, Ivy, Min, and Dean, and An, you will get an error message. But for those who have installed that optimization toolbox, you're going to get what fsolve does. It solves a system of nonlinear equations. So it can be one equation, 2, 3, 5, 100 equations. And it's a nonlinear system solver, and the fsolve MATLAB function takes as an input a function that we have to give it, like that has a residual, and an initial guess for that it solves this. So technically or intuitively, folks, what this does is you're defining this equation as a residual equation. You bring all these to the other side, and then you're trying to have 0 is equal to this minus that, and then you give an initial guess, like y bar is like 0.5, say. You stick in 0.5 everywhere, and then you let the solver do its job to solve this equation numerically. That's what's going on here. And then you get lots of information about this, and it is introduced in the so-called optimization toolbox. So that's what you need to have. Now I want to make sure, let me just go here and let's see whether we can identify where you guys need to install this on your computers. Let me just try to see. It is typically there we go. Let's see. No. I'm looking now for the place that I can show you where you can add a toolbox. Okay. There is a way to do this. So these are all my toolboxes, but I wonder whether you can quickly identify which tab you guys have to click to add a toolbox to your code, to your MATLAB. That's what I'm looking for. How do I add a toolbox to MATLAB? Add-ons, get add-on in the home tab. Perfect. All right, guys. So here's what you have to do in the afternoon. You're going to go to your MATLAB, and then you go to add-ons and get add-ons. That's what you have to do. Okay. So we need to first find the place where we have the add-ons. There we go. I see. Okay. So you go to your MATLAB, and you're going to have this add-on a button there. Right? So you click on that add-on button, and you have to get do this, and then it's going to open a picture like a window, and it's going to take a little bit of time depending possibly on your web connection. No, don't do that. Can you close that, please? Sorry. So you want to hit that down arrow here. You want to hit that down arrow, and then you want to go and you want to manage add-ons. There we go. Okay. So you want to hit manage add-ons, and then you have all these toolboxes, and you must have there must be a way for you to say get add-ons. Okay. Click on get add-ons on the top right, and then you can select a particular toolbox to install. Okay. I think that's what's going to happen here. So you can then search for the optimization and then you hit enter, right? You put optimization on top there, and then here, and I have installed, and you may have not installed it, right? So that you will find then a button install. Okay? That's how you have to try to do it. Okay? So you know, you will have, you know, you need to kind of install that. I hope that's going to, you know, be possible for you guys to install. Okay? Another way of sometimes how I typically do it is when you go to your applications tab, and then you go to MATLAB. Okay, you go to show package contents. So you go to your MATLAB installation. I sometimes, you know, what can happen is if you double click on this activate app, okay, that then it will open a user dialog where you can select more toolboxes in the installation process. So when I double click on the activate one, I'm going to get all this stuff, and I think, yeah, and you need to log into the account, and then you can choose more toolboxes as well. All right. Anyways, that's basically the task for you folks in the afternoon, to make sure that you have those that toolbox on your computer. Let's go back then to MATLAB here. Okay, so what is this? What is this fsolve now doing? So fsolve is an inbuilt MATLAB function, right? And it basically you know, takes an equation ZZ, passes in all the, you know, parameters, and it's going to drive the residual of the equation to solve to 0. Okay? And what's the residual function? It's this one. It's this little helper function. And so this is the find steady state. It's just going to drive, you know, the residual, which is defined here as f, right, to 0. So this is an equation from our model. This is a production function, if you like, I think. And it's going to drive that f to 0, and once that f is driven to 0 numerically, you have solved for the steady state, and as an output, you're going to get, you know, the output there. That's the idea. Okay. So long story short, this thing, this functionality, numerically calculates output. Okay, that's the basic bottom line. Any questions to this?
Can I have a quick one? Like previously in other lecture, like we got taught after we linearize everything, like put into system of matrix equation.
Put in the system of matrix equations?
Like all the linearized equation, we put it in matrix form, right? And then we have to check whether the Blanchard-Kahn condition is met before.
Oh, I see.
So
that's not here any longer. No, because this is, everything is non-linear. Although Blanchard-Kahn, you know, thing doesn't apply any longer, right? Because Blanchard-Kahn is based on a linear system of equations. So you will see something like explosiveness or non-solution, but it's a different solution solver, and there's no Blanchard-Kahn or anything like that because it's a non-linear model.
So this way of solving can be applied for both non-linear and linear?
Yeah, absolutely, absolutely, absolutely. So in fact, if you write in a linear model and use the solver we are going to use, you're going to get the same results as with the, you know, with the linear solver. So it's more powerful, it's more general. Just to make sure, what we're doing here is we're just solving for the steady state. We have not yet solved for the paths of the variables, right? This is just for the steady state. But importantly, the idea of driving down residuals to 0 of the equation, that will come back when we solve the model. That's the idea. Okay, any other questions? All right, so what else do we got then here? Well, then we are back into the normal linear world. We are calling the residual, we're calling the steady state, and then here is the little different syntax. This is already kind of gunning up on the idea of we're going to solve the model differently than before. Right? If you compare the shock statement that we had, you know, on Friday, that shock statement looks different than this shock statement. So with the solver that we're going to use, the shock statement is going to look different. So we're going to define that, you know, this EB, the shock to the discount factor, you know, it's going to have, you know, a one-time shock in period 1 that lasts for 1 period, and this is the value of the shock we're going to consider. That's it. It's a different, and we're going to play with that, you know, in a few minutes of this. And now comes the big important part. now comes the perfect foresight solver. So this is the new solver. It requires a setup, and I'm going to talk about that in a second. Okay? So it requires a setup, and then like in the setup, in the sense of if you want to use that solver, that nonlinear solver, you need to prepare it, and essentially you need to dump in at least one thing, namely for how many periods do you want to solve the model? How long is the solution transition path? And here it's 500 quarters. I'll talk more what that means. And then comes the holy grail command, perfect foresight solver. That's it. So I want to put in a return here afterward, folks. So everyone whose computer can do this, put in a return. And then let's run this code. So maybe type in close all and put in CLC. And then you're going to write in nkc underscore no trends dot mod semicolon. And then you hit enter. And I cannot do this because I'm not in the same folder. Or I have mistyped something. nkc no trends dot mod. Aha. What's going on here? What's going on? Oh no, please. Do I? Of course. I forgot to tell use Dynair. Okay, so my it's a Monday morning. I forgot to put in Dynair, of course. So you need to have Dynair no trends. So if you hit enter, then what you're going to see is almost nothing. Okay, so what are you going to see? We're going to see that we're going to see that we're calling, we're getting 11 equations, the standard Dynair output. Okay, and we're going to get whether our equations are solved at steady state. So these are the residuals. So we are taking the numerical solution for the steady state, and then we're dumping them in here. Okay, to see whether all the equations are satisfied in steady state. And we're going to get the residuals, okay? We're going to get the steady state numbers. And then we're also going to get the Blanchard-Kahn eigenvalues that Min was asking for, but they're not going to be used. It's just a check that if you linearize the model, Dynair does it in the background. Dynair linearizes the model as a test, and it's then computing. If you linearize the model and you calculate the Blanchard-Kahn, are the Blanchard-Kahn conditions satisfied? Although the solver is not going to use any of the linear stuff. So you could make sure that once you solve a non-linear model, that's saying, okay, let me linearize it, will I get a well-defined rational expectations equilibrium? And then, the only thing that's now happening here in the solver that you will see is this one. This is the output of the solver. That is the output of the solver. And the reason why, this is a hidden gem. It's a very powerful solver. But it's a little less known in the Dynair profession because it doesn't have all this fancy long output that we discussed on Friday, right? When we use on Friday, when we solve the model with the stock simul, we got this tons of command window output. And we got tons of pictures popping up, right? Remember that? With the nonlinear solver, you get none of that. You literally only get this, and everything else you have to produce yourself. And that's why this solver isn't so widely used and known, basically. Okay, because it requires it's super powerful, but it requires some more own work that we have to do. So now I want to introduce you, of course, what that solver does. Before we do that, let's do one fun thing, namely, for all the people whose computers don't work yet with the optimizer, let's do the following. Let's go to line 118, where we're solving for output by calling that function. Why don't we just put in the number 1 here, semicolon, and 2 forward slashes. So let's comment out the usage of the steady state file. Let's comment that out. We want to just comment that steady state file out. We're not going to use it. And just going to say the steady state of output is equal to 1. And let's see what happens. That's the basic idea. Let's just see what happens when you then run this file. I'm getting an error message, and I shouldn't be surprised by that. And here is how you can always diagnose whether you did the math correctly in terms of the steady state. Because what Danier now does, folks, and this is all, it's a beautiful check. Danier takes now all these numbers, right? I mean, these are numbers. These are parameters. So the left-hand sides are all numbers. Okay? And then Danier goes and sticks these numbers in everywhere into the equations here in steady state. So the number for x, it sticks it in there. The number for y, it sticks it in there. And then it computes what is the residual of this equation if it stuck all the numbers into this equation. Is this equation equal, like with equality, or is there a residual in this equation? So is the left-hand side different from the right-hand side? And this reset command is going to give you exactly that. Okay? This reset command tells Danier, take the steady state solution that you think you have calculated, stick it into the Andorras equations. Okay? And if you look then at the residuals, you're going to see many of them actually, oh yeah, many of them are good, except one is kind of, it's not zero yet. Okay? And that indicates there is a problem, that you haven't found the steady state yet. And Danier tells you where the biggest residual is. Well, it's in the marginal cost equation number 6. So then you go to the equation number 6, okay. Go there for the steady state numbers. Where is this equation for number 6? And let's count. 1, 2, 3, 4, 5. There we go. This equation isn't solved yet. This equation has a residual. And then it requires a little bit of expertise, but you at some point are going to find out there must be something with y. So we use the number 1 in our initial guess, right, or in our steady state. That's a problem. Can you now, for those like min and d, can you now get? Do you get this output with the reset? Yeah. Okay. So now you can, do randomize. Now you can say, okay, let me take the number 2 here, okay? And then you rerun your code and see how this residual changes. Oh, now you see the residual becomes negative. That is fantastic. You're looking, right? I mean, that's what you want, right? In terms of the steady state. So let me write this. Just make sure you're going to be on top of that 100%. Okay. So, right? So we want to solve. We want to solve this equation. So we want to have the reset is equal to the square root of y bar to the cube minus y plus x squared minus y bar minus 1. We want to solve that equation, right? And then we tried, when y bar is equal to 1, we get that the reset is equal to 0.034 whatever, right? And then we tried y bar equal to 2, y bar equal to 2, and then we find that the reset of this equation is equal to minus 4.2. Right? So by having different y's in this equation, we see that the residual of this equation either is positive or negative. That's fantastic, because we want the residual to go to 0. Right? So we know if we now search between 1 and 2, and we narrow this, at some point we're going to get numerically to the residual of this equation being close to 0. That's what fsolve does. fsolve does exactly that. It uses a Newton algorithm. So for those who did computer science and math, right, it uses a Newton algorithm to drive that residual to 0. That's what's going on. So that fsolve, okay, fsolve, solves for y bar such that the residual is approximately 0. Such that the residual is approximately 0. That's what fsolve does. Okay. Any questions? So, everyone, maybe you want to copy that. So let me go back then to our slides, to the computer, right? And let me then uncomment this line and see what value of y does solve this. Okay? So by rerunning it, what you will learn is that then the value of y that does solve this equation exactly is 1.01504. Okay? That's what fsolve does for us. So if we take that, you don't need to do it on your computers, but if we take that number now, 1.0515 and we dump this in here and comment out the steady state search routine, then what you're going to find is that the residual is driven to 0. I mean, it's driven to approximately 0. Again, this is not precise enough because I copied only 4 digits or so, right? And those 4 digits or 5 digits, they're not precise enough. I should have copied 7 or 8 digits, and then this thing is exact. Good. So that's the bottom line here. Right?
But can we adjust the number of digits?
Yeah, we can. But you can always do this. So the way this works in Diner is you're typing in format long. If you type in format long in Diner or in MATLAB, and then you're printing out maybe 2 divided by 3, and then you're going to get more digits. Okay. If you type in format short and you type in 2 over 3, you're going to get fewer digits on the screen. All right, but in general, you should always use then, of course, because this is automatic once you use the function. Okay, it's just what MATLAB displays. When MATLAB does calculation, it always goes to machine precision. Okay. Great. So then, I think everybody should understand now how the steady state business works and how powerful it is to work with nonlinear solvers. Okay? In case you have a model where you cannot solve for the steady state explicitly, as these guys have. Good. So then, I owe you the $1 million explanation now. What is this solver doing? Okay? How does this thing work? Okay? And that's what I want to, go through and count with you now, and explain and go through. So let's do a couple of notes because that's kind of important. Okay? Let me go to our slide deck, and since we are in this Diner session, why don't we, write a little more on this Diner live coding session, but now, of course, with the new code kit that we have. So this is going to be now Diner NKC no trends dot mod session. Okay. So the first task is what we already did. So the first task number 1 today was to examine and run nktrends.mod. Okay. Examine and run nkc_trends.mod. So we did that. Okay. We studied the steady state routine. We studied the steady state, non-linear steady state solution. Okay. So we studied the non-linear steady state calculations using MATLAB's fsolve function. All right. So that was the task that we did so far. And next, and that's going to be important now. Okay, study the nonlinear solver. The nonlinear solver to solve the dynamic model. The dynamic model. That is the next task. Okay? So we have to, study that nonlinear solver, how that is actually being done. Okay? Now, to do so, in task number 1, that solver has a particular name, okay, and it's called. The name of it is called Perfect Foresight Solver. semicolon. That is the $1 million solver, right? So rather than using the stock simul, right? Rather than using the stock simul solver to simulate and solve the model, now the new solver we're going to use is the perfect foresight underscore solver. Okay? So what is this? It goes back to a very famous paper by Fair and Taylor. So this is the so-called Fair and Taylor 1983 Econometrica. ECMA is for Econometrica, a paper. And it goes by different names. So some people call it the perfect foresight solver. That's where the name of the routine comes from, right? So this is going to be called perfect foresight solver. It also is called sometimes the extended path. So some papers, some literature calls this the so-called extended path solver. Talk about that, what that means. And yet other papers call it the time stacking solver. It's called the time stacking solver. Yet other papers, so this is the whole, this thing basically has 4 different names in the literature, and they all mean the same thing. The last object that's often called is called the 2-point boundary value solver. It's the 2-point boundary value solver. So these things mean all the same. The 2-point boundary value solver, the time stacking solver, the extended path solver, or the perfect foresight solver. They all mean the same thing. So how does this work in practice? Okay, so here's an example. Okay, here's an example how the solver works. Okay. Suppose you have the following nonlinear dynamic equation. So suppose you have an equation that reads like this: CT is equal to CT plus 1 to raised to the power of 0.3 times xt, the square root of xt. Suppose you have that equation. That's like, I just made up this equation, but suppose you have an equation like that. It's nonlinear and it's dynamic. Okay. How do you solve, and then maybe so how do you solve an equation like this with this solver? Well, the solver literally takes an equation and writes it down for period 0, for period 1, for period 2, for period 3, for period 4, and so forth. So what the solver, and that's where this the idea of the so-called time stacking solver comes from. Time stacking means you're stacking this equation over time. So the solver literally writes, for t equal to 0, so for t equal to 0, you're writing C0 is equal to C1 to the 0.3 square root of x0. Then you're writing this for period 1. And this is going to be C1 is equal to C2 to the 0.3 square root of x1. You're literally writing the model equations period by period. And you're going to keep doing that for some capital T. You're going to say, there's some capital T, C capital T is then equal to C capital T plus 1 to the 0.3 x capital T square root. Now assume that the x, for instance, is exogenous and a shock. Okay? So this is not the x in our model, it's just for this example, suppose this is exogenous and this is a shock. So this equation is perturbed by a random shock that happens on x, and it gives you the dynamics of consumption. So now, how does the solver now work? Well, the solver now does the following. It computes the residual, and we use a different color, right? it moves the c's to the other side. Everywhere it moves the c's to the other side. And then computes a residual on the left-hand side of the equation. So it computes, conditional on, okay, so that's basically what it is. It's a residual-based solver again. Okay? And now comes the important part. So suppose you're having this x, you have a time series for this x, because this is exogenous, this is a shock. You have these numbers. And then the solver says, okay, I have capital T equations. Can I find the trajectory for consumption, C0, C1, C2, capital CT, so that all the equations hold in orbit using fsolve? That's what's going on. So the solver does the following again. Conditional on a time path for x, it's trying out different values for C0, C1, C2, C3, C4, C capital T, so that all these equations hold. That's the key. That's the solver idea. Now notice there's one problem. There's one problem. How many equations do we have? Well, we have capital T equations, right? So the number of equations is equal to capital T, right? So if T is 100, we have 100 equations. One equation for each period. How many variables do we have? What's the number of variables? What's that? T? Or 1? T minus 1? Okay, we have T or T minus 1. Another one? Somebody else? How many variables do we have?
Because we have CO.
Yeah, wait.
T
T plus 1. There we go. This is our big problem, right? Because this is an Euler equation, right? And in Euler equations, we always have one period ahead looking this, right? So we have, with capital T equations, we have capital T plus 1 endogenous variables. Okay. So that's the problem. That is the problem. We have one variable that looks too far. And this is then why this model, this solver makes one assumption that after capital period T, the model assumes we are back in steady state. So the idea is that when you are in steady state in capital T, then of course you're going to stay in steady state in capital T plus 1. That's the key idea. So we have T plus 1 variables here.
The number of equation should be T plus 1.
What's that?
The number of equation is T plus 1.
Well, the problem is if you say, look, let's do T plus 1, then you're going to get T plus 2 here.
I mean, like, because we start from T equals 0,
Oh, now I see your confusion. I got you. Sorry. No. It's my mistake. I'm very sorry. So actually we have T plus 1 equations. Sorry about that, right? Because I did a bloody counting mistake. So this, of course, is T plus 1 equations. I'm very sorry. So we have T plus 1 equations, but we have T plus 2 endogenous variables because of this one. Sorry, right? So we have, thank you so much, Hui, for pointing this out, right? We have T plus 2 endogenous variables. Okay? I should have started with T equal 1. That would not have happened. Okay, anyways. So we are lacking one equation, and the common assumption is that after period T plus 1, once you are in the steady state, you're going to stay in the steady state thereafter. Okay? It's like you have converged to the steady state, and you're going to stay in the steady state thereafter. So the assumption that the solver does, the assumption number 1 that the solver does is, you are, C capital T is equal to C capital T plus 1. That's the assumption. Okay? So in other words, you may be far away from the steady state of period 0 and you're converging to the steady state, but once you have converged to the steady state, then this one is equal to that. It's like, if you're back to steady state, you're going to stay back to steady state. So that's the idea. So that's the important assumption number 1. Notice then, your number of variables you're solving for is going to equal the number of equations. That's the key. So with this assumption, right, you're going to have the number of equations equals the number of variables. That's the idea. So that's the first. And then the second assumption that has been done in this literature is that there is no uncertainty. That's why it's called perfect foresight solver, right? In other words, you know the trajectory of the shock. That's why it's called perfect foresight. You know this trajectory of shocks, so it's certainty equivalence. Okay? So the assumption number two is there is certainty equivalence. Okay, right? So you know the trajectory of the shocks. So you know the path of x0, x1, x2, etc. Okay, that's it. So then, with those two assumptions, you use an F-solve, right? You use the same idea as with the steady state. You use an F-solve on these 100 equations to drive the residual on these equations to 0. That's it. So then, and that's what's done in practice behind the scenes, you're going to use F-solve or any other solver that you would like, to drive the residuals on the t plus 1 equations to 0. And that's going to give you the path for C0, C1, C capital. That's the idea. So, with this path, you use F-solve to drive the residuals on the t plus 1 equations to 0, and that gives you then the path for consumption. So you want to copy this. Notice how powerful this is. Right? This does not assume you're working on a linear equation. This is a completely nonlinear solver in that regard. So the full nonlinearities will be, born into the dynamics of consumption. And you will get, so to say, that, those residuals. So maybe let me write this. So we're going to have resid in 0 is then C1 to the 0.3 times the square root of x0 minus C0. And you're going to have the resid in period 1 is then C2 to the 0.3 square root of x1 minus C1, and so forth. Okay? So you're trying to get all these residuals to 0. And once you have done that, you have solved for the dynamics of this model in response to a shock. Okay. Beautiful. Now, as I told you, this solver has different names. One is this perfect foresight thing that comes from, you need to know the trajectory of the shocks on a given point in time. It's called also the extended path by a similar idea. Time stacking, you time stack the model equations. And this 2-point boundary value solver, what does it mean by the 2-point boundaries? You know the beginning and you know the end. That's what the 2 boundary values are, right? So you know the t minus 1, in this example it's trivial, you know the t minus 1 value, the steady state, and you know the t plus 1, which is the end period. That's why these are the 2 points. And then you're solving for the dynamics of the model between those 2 points. So that's why you have these very different types of names for the same thing. So if you read papers and people write about the 2-point boundary, the perfect foresight, the time stacking, it's all the same object. All right. Any questions on this? So let's go online then. And let's go for the Dynair website, website, and let's do a little bit of research on the Dynair. So let's go to documentation, okay, and let's do a little research on this, and let's type it into the search field perfect underscore where is it? There we go. Perfect. No. Let's try to search already for perfect, and then we will get this one. Here we go. So there is the search results, and we want this one. Okay, the perfect four-side solver. There's different objects, with expectation errors and whatever, but I don't want that right now. I want this perfect four-side solver. Okay, and that's going to take you to a documentation how to use it. Okay, and as with any other Diner functionality, right? You have these options that you can put in, if you like, into the solver. You have to do a little bit of either you do this or you do the setup, okay? So either you put in options into the solver directly, or you're running this perfect four-side solver setup. Those are two equivalent ways. And then you're gonna get all these options that you can put in, okay? There's different solvers, you can use a Newton algorithm to drive the residuals down. That's an F-solve. But there's like other numerical ways to drive down residuals on nonlinear equations. Okay? And that's all what these things are. The sky is really the limit, and it's beyond the task of our course to go into the details of what this kind of solver does. But it's very powerful in many, many ways. It can solve models not only that are nonlinear, but also models with occasionally binding constraints, like the zero lower bound constraint. Right? Like when the interest rate cannot go negative, you can literally put in a max operator in some policy function, into the policy rule. You can solve models with banking where you have occasionally binding constraints, where, say, a bank hits a capital buffer constraint, like a Basel III constraint. So any nonlinearity that you can dream of, be it either because you have funky nonlinear functions, or you have a lower bound constraint on an interest rate, or in a finance model, this solver can handle those exactly. So why is that? Well, if your equation, for instance, includes a max operator, well, you're just going to time stack that object in, and you're going to solve this exactly. And so long story short, that's really why this is so powerful, and it has gotten a lot of attention, and the profession is realizing how powerful this thing is. Like here's, for instance, an example with a lower bound that the interest rate cannot go negative or too negative. That's how you would import that in. Okay? All right, so lots of fun stuff, folks, right? And so let me show you how this looks like in the computer codes. Okay? Let me show you how this looks like into the computer codes. And the one important thing is here is this setup option. So we are solving this for 500 periods. So we are taking the model and we are stacking it for 500 periods. So we go from t equal to 0 to 1, 2, 3, 4, 5, 4 until 499. So we are saying when there is a shock hitting, the economy is back to steady state at the latest after 500 periods. And my advice to you is, if you're working with this, always pick a number that's rather too high than too low. Go for a number that is too high, so you're well into the steady state. Maybe you're already back to the steady state after 100 period, rather than going too short, thinking of 10 periods is enough. And then you just hit that solver, that's it.
And choose the number of periods.
Yeah, absolutely. So you can just by, for instance, if you are setting this equal to, to 1,000, say, then you're going to use 1,000 periods. Capital T is then 999. Okay. If you're using 10,000, then you're using 10,000 periods. If you're using 10, then you're assuming that the economy the transition is happening in 10 periods.
So it depends on our assumption.
It depends on your assumption, exactly. My advice is, if it's the modeler, use 500 or more. That's often the best. And then that's it. Okay. And then when you run this code, successfully, you're going to see that this is the only thing that you're going to get. This is the only output from the solver. Okay? And the only output is that Diner now uses an F-solve thing to drive the residuals down. And it's, you know, we take our model, we literally take now these equations, okay? All these equations, we're taking our 6 equations and we stack them for 500 periods underneath each other. It gets a big problem numerically. And then the idea says, okay, if there's a shock, we're just going to find the residuals that, you know, make all these equations hold. Okay? And the output is this one. So in the first iteration, the biggest residual is 0.1. Okay, so among all these 500 equations, 500 times 6, we have 3,000 equations, right? We have 6 equations, and we're stacking them for 500 periods. So that's like 6 equations times 500 periods. We're having an equation system that's 3,000 equations and 3,000 unknowns. That's huge. And the biggest residual at the initial point is 0.1. It's typically the shock you're inputting. Okay? And then you know, the Danier does the F-solve, it goes iterations, so it does the Jacobian, so it takes the numerical first order conditions and looks where can I make the biggest progress. And so in the first iteration, you see the residual gets already very small. And then in the second or third iteration, the residual gets even smaller. And then at some point, you know, we have numerical precision at e to the minus 7 often, and then all the residuals are numerically 0. And you see it's incredibly fast, 0.2 seconds. That's it. Okay, so that's how you can, now we have solved this model. And what did we solve? Well, we solved this model subject to, you know, the shock that we put in is this demand shock. Well, we put in a demand shock, and then we have solved the model. All right, any questions?
Sorry,
Yeah.
in this model we need the perfect foresight because our climate model, because of the carbon damage, so everything is brief, right?
Yeah, that's
but,
right.
But say if say for my model, if I don't have that problem, but
Yeah.
I just want to solve it non-linearly, and I just need then the first part of the part. Or
The first part of the, what do you mean by
meaning like I don't put in the transition.
Yeah.
But I assume that there's always a steady state, and I can still use this solver to solve it, right?
But what do you mean then by solving? Do you mean like, I mean, solving means always a transition, right? When you want to consider a shock. Where you're saying you don't want to consider a shock, you just want to compute a steady state.
Oh, if I just want to compute the steady state,
Yeah.
I can just use the F solver.
That's right.
Okay.
That's right. So the F-solve you can always use to compute a steady state. This now solves for the entire transition of the temporary shock. That's the difference. Okay. So importantly, there's 2 types of residuals in this model. There is you have a shock and the economy adjusts over time. That's what the perfect foresight solver does. But the steady state also has a residual, and that's where you use the F-solve as well. So you know, that's here. Okay. So some models, the steady state is trivial, you don't need the F-solve in the steady state. If your steady state is very simple, you don't need any F-solve. You can compute this closed form. It's just that if you have a model where the steady state is kind of complicated, then it's super useful to have, because the F-solve, everything we learned about that F-solve, that also applies for the dynamic paths. Is that helping? Yeah? Okay. So the key is really the perfect foresight solver is doing the trick. Now, we don't have, the thing is, there's no screen output except for this. But of course, in the background, Danier has now solved for the entire transition path of the economy. The complete set of paths in this economy. So how do we think about that? Where can we see this? Where is this? Where are the results? Okay? So that's why I want to do another task now with you. Namely, the task is going to be the following. Task number 2 that we want to solve, that we want to do is we have to learn. Okay, so now I'm going to do task number 2. We have to display or graph the solution or the simulation output. Okay, we have to learn where do we find that? How do we graph it? Okay. So we want to graph the output of the solution, i.e. the impulse responses. Okay. The simulation slash impulse responses. Okay? That's what we want to do first. And then we want to do, experiment with different shocks. Experiment with different shocks. Okay. You want to experiment a little bit with that. Okay. And then you can do more, right? I don't know whether we will be able to do this. I think we need to go at least 5 minutes longer because we started 5 minutes late and I want to finish this, but you could do lots of other experiments. You could add additional variables, additional variables to the code, to the model, additional variables to the code. So these could be, for instance, emissions, etc. Right? Because we have, this model has condensed everything into 4 equations and 4 unknowns by substituting out like the level of emissions and so forth. And you can just later on just add an equation to this code to then, calculate the level of emissions and display that. All right. So that's going to be the task number 2, and let's do that together, I suppose. Graph output, impulse responses, experiment with different shocks, and add additional variables in the code. So how do we do this? Let's go back then to our MATLAB and examine the last couple of lines in this code that we have commented out. This one here. So where can you find the output, the solution that Danier has calculated? Well, it's in this OO_endo_simul. That's where the solution is. So let me type in, this OO_dot_endo_simul. If you type that in, you see it's a huge matrix. It's a huge matrix with lots of stuff. So let me do size OO_endo_simul. So this gives you the size of the matrix that is stored there, and you see it's 11 by 502. So we have 11 equations, right? So those are our 6 original nonlinear equations plus the shocks and the definition of D. That gives you 11 equations. That's the rows. And then we have 502 columns. We set t equal to 500, and then Danier adds the steady state initially and the steady state at the end as 2 extra lines or columns. Right? So in other words, if you change to 500, this thing is going to change. And it has all the simulation results. And then what this code does, it generates a subplot, a 2 by 3 subplot of 6 variables, and then displays the first 6 lines. So the first 6 lines in endo_simul, it displays that as a plot. That's what this code does. And again, what are the 6 entities that we have at the beginning? So let's take a look at the mod file code. Right? So those are inflation, the interest rates, output, consumption to output, carbon, and that's it. 1, 2, 3, 4, 5, and marginal cost. So we're going to plot those 6. And then later on, we can plot many more things if you like. So let's do that. So let's now uncomment, let's uncomment these, take out the return, and now rerun this file. Rerun this file, and then you're going to get this graph. And so what is this graph? These are the impulse responses to a demand shock in this economy. These are impulse responses to a demand shock in this economy. Everything is non-linear. So these are not in percent deviations, but these are in absolute units that a variable is defined. So let's do the following. We're going to take a break now. And I want to do one thing before we go into the break. Okay, so we know that there's 11 variables. What I want you guys to change, let's do the following. We know that there's 11 equations. Let's put in, instead of 6 here, let's put in 11. So let's graph the entire endogenous variables that we have. And in the subplot, please do 4 by 3. Okay? So type in 11 there, and type in for the subplot 4, 3. And then rerun this code. And then we're going to take a break, and then we're going to discuss the impulse responses after the break. So what you should have after the break is something like that. Okay? Does everybody get that type of picture? That's what you need to have after the break. And then we're going to go discuss this, and then we're going to play a little bit with other shocks and learn how things are done. Okay? That's the bottom line. Good? Break. Have a break. All right, perfect. Have a break, everyone. We'll see each other in like 15 minutes, so 5 past 11. Okay? We're going to continue then.